No. Oh my gosh. All right, so I'm not going to do my big speech yet because we only have, I'm missing 13 people still. So no one has any questions. There's the, did anyone try the practice 2.1 through 2.6? Did that go okay? Did past Jeff do an okay job on the solutions video? Did anybody look at that? That was Jeff from at least one semester ago, if not two. I don't know. He was crazy, man. Okay. So just to remind you guys, the quiz today is all of chapter 2. So if you look at the standard deviations worksheet and the 2.126 practice stuff right here, and of course there's a solutions video for that. Oh, I was supposed to put something up here, wasn't I? Was I supposed to put the what we did in class here? I think so. Jeff, you suck. You suck, Jeff.
On the actual quiz, how on the standard deviation handout you put the variance formula, will that be on the actual quiz or do we have to come up with that formula?
No. So on the actual quiz, in fact, let me show you this. Has anyone even tried to open the quiz? If I were you, I would have tried. Right? Why not? Right? Why not? You know, let me get us thoroughly started on it. And I can see this, but you can't. Ha ha ha. Ha ha ha. But let me show you this. Shit, what did I just do? All right. Once you click on take the quiz, an hour and 20 minutes. Oh, I got to change that. I'm so happy I'm doing this. There are 2 sides to the quiz, and I did that just to give you a lot of room in case you want to print it out. You with me? And the formulas are on the bottom of the first page. Now, what formulas are not there? Stuff like class width. You got to know how to find the class width, right? The range. You got to know how to find the range. I don't know, but I got z-score formulas there. I got standard deviation formula there. Cool. Yeah.
Thank you.
You're welcome. And while I'm doing this, here, give me a minute. I forgot to increase the amount of time I gave you on this one. There you go. You got more time now. Oh shit. Did I do that right? I don't know. All right, guys. So that's the quiz today, all of chapter 2. And if nobody has any questions on that, I'm going to make the quiz due tomorrow at midnight. So this time, like I said last time, this time we will have class before the quiz is due. I can see who's taking the quiz, so don't be in class and take the quiz. In fact, don't take the quiz during class. Don't skip out on class to do the quiz. I mean, that doesn't make any damn sense. Are we only allowed to use one formula? I don't understand. One formula to do standard deviation. Oh, there is another formula that's a reorganization of the standard deviation formula that we used in class. Yeah, I think it was you that did that on the homework? That I used to actually show that formula, but there just isn't quite enough time in the summer to slam that at you, because it kind of loses the concept. But technically, a different formula is fine, but you have to show me the table. You have to show me your work. Yeah. Class width is high minus low divided by the number. No, definitely not. What is, how do you figure out the width? So I like the high minus low, right? Divided by
the number of classes you want to have.
Classes, right? Yes. After we fix assignments, when can we learn if it's still correct or not in our grade? As soon as I grade them, which I might not do till the end of the semester. My main priority is new homework, which is constantly keeping me busy. If you have stuff on corrections that you have questions about, or you just are like, I want to see if I get this right now, you can let me know and I'll take a look. Otherwise, I'll grade it if and when I get time. The thing for me with corrections is I want you to have a reason to slow down, to look at what you got wrong and figure out why it was wrong. That should all help get ready for tests, get ready for the midterm, get ready for the final. If there are things you can't figure out on your own, then you ask me in office hours. So by allowing you to make corrections, I'm hoping that kind of forces people to ask why they got something wrong, you know, a little more motivation for that thing that should happen anyway, but sometimes it doesn't. Does that make sense? I was replying to somebody in the in the chat. All right. In the homework, Jeff. Where's your brain? I don't know. Anything else? Yes?
I have a question about how to get your table to like square your tables or your list.
In the calculator?
In the calculator, yeah. Because I remember you did something, and then every time that I try and do it, I get the error thing. So I just forgot that step to.
Do you get data type error or something?
Yeah, something. Yeah.
Oh shit! I think oh man, this sucks. Hold on. I think my license just ran out for my TI. Yeah, it did. All right, so I'm gonna have to go old school. All right. Shite. So, nice thing is, let me see if I can do this with the way I've got things set up. Well, shit, I'll just do this. All right. Let's see, that's very blurry, right? Okay, I know. There. All right. So let's say I've got stuff in my lists. Can everybody see that okay?
Yeah.
Okay, so let's say, let me put some stuff in my list. And let's say I want to square everything in that list. So all I have to do, now look, if I do this, it's going to give me that error. Why did it give me that error? Because I'm trying to throw a whole list into one spot. So that's the most common mistake people make. So if I have to go up to list 2, I want to put a list into list 2, don't I? What do I want list 2 to be? I want it to be L1 squared. Yay! Is that all right? Is that the error you were getting?
Yeah, it was. Okay, thank you.
Be really careful about
it's very technical.
You are. All right, let me make you guys all wonder about your prescriptions. Hold on. Where am I? All right, hold on. There I am. Let me go to a different universe. Oh my gosh. Who is that guy? Oh, that was really weird. Sorry. I like weird, period. So, that's a good question. For the box plot, you don't want us to do the outliner? Oh, outlier? Maybe? Just the 5 numbers. So, all a box plot is representation of the 5-number summary. It's a visualization of the 5-number summary. That's what a box plot is. And of course, we saw in that one problem, especially with Germany and China, we saw what could happen with box plots when you have a lot of repeats. Really strange things can happen, right? Is that all right? Does that make sense? Random chatter out there? Okay, I'm gonna go with yes. I'm gonna go with that was perfect, Jeff. Okay. Anything else, guys? Okay, all right. If there's nothing else, all right, we're gonna go back into chapter 3. I got a little bit left to discuss. There's one homework. The outlier. What do you mean outlier? So an outlier. So the max could be an outlier, but outlier is not a standard thing you find with box plots. So I'm not sure what you're talking about, unless you have a specific problem that you have a question about. Maybe? No? Yes? I'm sorry. It's okay. You can ask. The book mentioned that some box plots
With
have dots.
box plots,
Oh, yeah.
you start the box at the beginning of the second quarter, right?
Yeah, you box off the middle 3 lines. So that would be Q1, Q2, Q3.
Okay.
Yeah. Yeah, and there are variations on the box plot idea. So the one we did was the most basic kind of box plot. So yeah, the book might have talked about different ways of handling certain things. Yeah, okay, all right, I like it. But none of the homework I gave you required a dot for an outlier. Yeah. Okay, okay. Anything else? Any other freaky things? Okay, all right. So yesterday we did a lot of probability stuff. We created 2 formulas, I believe, if I remember correctly. So let's kind of recap what we did yesterday. The results of what we did yesterday anyway. I'm sorry, dude. All right, let's see. I need a much bigger studio. That would be nice, but too bad. And where am I? There I am. Yay. Why is everything janky? My room, my house is tilted. All right. There we go. So yesterday we figured out, oh, look at you, Purple. You kick ass. We did a problem, and then we came up with this formula, right? So do I need probability formulas for any probability problem? Not for every, for some, but not for every problem. So today we'll talk about what problems I have to use a formula for, because again, probabilities are based on counting shit. So if I have everything there that I need to count, I don't need a formula. We also did this formula. Become a B. There. Let me focus on this here for a minute. So this is the one time that the bottom changes because I'm given more information. So given that B happened, so the bottom has to be related to B. It's got to be out of those things that are B. A given B, yes, good point. Let me show you this. I can't remember off the top of my head if the book actually uses this, but the symbol for given is a straight up and down line. Now the really bad thing about that is people think this is divided by. This is a straight up and down line. This is just the symbol for given. That's what that is. So thank you. Private chat.
How many decimals should our percentages go to? 2 or 3?
Does anyone know?
3 for probability?
Wasn't it 4?
4, yes. And there is a reason. It's not just me going, and now this one's going to be 7 decimals. No, there's a reason. I'm getting you ready for something. But in general, it's better to not round too much until you're at the end of a problem. But there's a reason I want you to go 4 places. Okay. Now let's focus on this for a minute. The given. Is anyone really bad at cards? Do you guys all know how many suits are in a deck of cards? Like there's hearts, and how many of those are there? How many? There's hearts and there's diamonds.
There's 13 of each, right?
13 of each, and how many total suits? How many
4
total?
suits.
Yes, good. Is everybody with that? Is everybody with that? So there's hearts, diamonds, balloons. No, that's Lucky Charms. Clubs, and spades. Yes? Yes? Is that cool? And then there's 13 of each, 13 cards in each. So there's 52 total. If anybody has an older sister, an older brother, you know there's 52 because you have to play 52 card pickup. Whenever they would just throw the cards, say, pick them all up. I might be talking from personal experience. Now, this is so beautiful for probability. And do you guys all know what the cards are? Well, let's say ace is 1. So it goes ace, 2, 3, 9, 10. What comes after 10?
Jack.
Jack.
Queen.
Queen.
King.
King. Right? I like it. I like it. Now, I mean, we could have a whole discussion about the problem up here culturally and historically and all that kind of stuff about why would the king necessarily be higher than the queen. We're not going to go there. This is just the way it is for whatever reason, right? I actually agree with that there's a problem here, but who gives a shit right now? We don't care. It's just the way it is. So if I picked one card, what's the probability that I get a king?
4 out of 52.
Good, perfect. Can somebody might have been thinking this, but can you understand why somebody might say 1 out of 4? I get this answer all the time for this kind of question. Somebody says 1 out of 4.
Because you can get a king from any of the 4 suits.
Well, there's 4 kings, and they're thinking you want to pick one of them. But somehow that means that you've eliminated the possibility you pick anything else, and you're assuming there's a specific king that you want. None of that's here. I just want a king. So how many things match what I want? 4 out of how many total things? 52. That reduces to 1/13. And I should remember what this is, but I don't. What is that if you divide it? 07.
0.0769.
Thank you. All right. So 7.69% chance that you'll get a king. Now, let me ask you this. What's the probability you get a king given that it's clubs? Oh.
1 out of 52.
No, because it can't be any of the 52 cards anymore. What do you know about the card that you picked?
Has to be clubs.
Has to be clubs. So how many are we talking about? 13. So out of those 13, how many is king?
1.
1. I like it. So
Is
we
that
threw
assuming-
out.
oh,
Go ahead, sorry.
Is that assuming that we're picking from a deck of only clubs and not just a whole deck? So you basically
No.
only giving 13 cards.
Even if I was picking from just, well, all right. This whole thing is assuming a fair standard deck of cards. Is that I understand? Now, what's interesting about your question is, on number 2, is as if I threw if I threw these out, right? Just throw them out. So now I've only got 13 cards. And when I threw these out, didn't I throw out 3 kings?
Mm-hmm.
That's why it's 1 king left out of 13 cards left. Your whole universe becomes this, and then this changes if I lost some because I focused on these. Did this change at all? This probability, did it change?
No.
Is everybody with me on that? Do you guys agree?
So
These
then-
probabilities. Go ahead, sir.
Does that mean that for the second one, someone is holding a deck of only the 13 clubs, not the whole 52 deck?
All right. So here's what it really that could be it, but here's what it really means. I pick a card and I look at it and I say, the card I picked is clubs. What's the probability it's a king?
Oh, then 1 of 13.
There you go. effectively what you said is the same situation, because when I say the card I picked is a clubs, you know it can only be one of the 13 clubs then. Does that make sense? So effectively it's the same as if I just went, no, there, I got clubs, was probably this one's a king. You're like 1 out of 13. It's the same thing. Maybe. In fact, you can see this reduces to this. These are the same situations mathematically. So let me ask you this. Does knowing it's a club change the probability it's a king? I already kind of asked that question, but not quite like that. Knowing a card is a club, does it change the probability it's a king?
No.
No, it doesn't. We see it right here. If I know it's a club, does the probability it's a king change? Nope. So would you say that the event king and the event clubs, would you say that they're independent or dependent?
Independent.
Independent.
All right, somebody's lost. What's all right? I need you to ask questions. Is everybody cool with the calculations we did here? Was it the explanation about the weird thing about throwing stuff out from the deck that lost somebody? Somebody's private chatting me that they're lost. You got to help me figure out what you're lost with. Is anybody not cool with the calculations we did? Let me know now. You can private chat me. You can say, I don't know what the shit you're doing right now, man, and I'm not going to call you out. Okay. So are you talking about the discussion that I think it was Petrina and me? I can't remember who it was asking me about, did I throw everything out except the clubs? Is that what you're talking about, that discussion? I guess. No? Or are you talking about the question I just asked? Okay, that discussion, forget about it. So given that it's clubs, so how many cards could it be? Only 13.
What makes something dependent versus independent?
And that's what we're trying to build to. That's what I'm trying to build to. I wanted to see if you could naturally figure it out yourself. Now, let me say this again, and then I'll ask the question again. Knowing that it's clubs, did the probability of king change? If I know it's clubs, did the probability of the king change? No. So would you call that independent or dependent?
Yes, it is, Mohammed. Yeah.
That was neat. Do they care about each other? Does king give a shit if clubs happened or not?
Yes. Right?
If it cared, wouldn't the number have changed?
Oh, that's true.
I really want this to make natural sense, why we call this what we do. Knowing it's clubs, did it affect the probability that it's a king at all? No. So the event king does not give a shit if clubs happened or not. You guys with me?
I'm having a hard time following. I guess in my head, it did impact it because there's only one king that's a club.
Look at the number. Didn't we get 1 out of 13?
Right.
And didn't we get 1 out of 13 up here?
Yes.
Aren't they the same number? So the probability is the same.
So whether or not it's a club or if it's the whole deck, there's still only 1 out of 13 chance that
There's
you're
a
going
1
to
out
pick
of
a
13
king.
chance it's a king. So
king doesn't care.
Does the event pick a king care? And I know I use that word weird because it's like, how can a card care? But hopefully you understand. Does it care if it's a club or not a club that I picked? No, it doesn't care. It doesn't change if I know it's a club. Let me see. Is there a situation that I won't get in trouble for? Let me think. I used to do this problem. All right, I'm just going to try this. Well, let me do a different one. All right. You see somebody walking towards you. You and a friend are walking. You see somebody walking towards you, and you don't know if that person is old or young. They're kind of far away, right? So you're like, there's a 50% chance they're young, 50% chance they're old. Is everybody kind of with me at the moment? Just subjectively? I don't know. I can't really see them well yet. And then your friend says, your friend's got really good vision, right? And your friend says, oh, that person has $1 million in the bank, right? I want everybody to be with me here. You guys with me? Somebody's walking down the sidewalk towards you. You and a friend are walking. You're like, I can't tell if they're old or not. I'd say it's a 50% chance they're old, right? Older than the average. And then your friend says, that person, I know that person, they have $1 million in the bank, right? Does that affect the probability that they're older at all? Is it, oh, I love you guys so much.
No, it doesn't.
I love you guys. All right, so this might be, of course it does. Okay, I mean, how old are most of the millionaires out there?
Old.
Okay, so if your friend tells you, all right, let me up the ante. Your friend tells you that the person coming at you has $20 million in the bank, right? Does that affect the chances that they're younger or older?
Yes.
Yes.
Yeah.
All right, so the example I used to give, just to get this one out of the way.
But that would be an and, not a line, right?
Say again, sorry?
That would be an and, not a line in between.
No, it'd be a given. It would be a given. Given that they have $10 million, because it wasn't that information that you were given? Did your friend give you that information? Given that information, that changes the probability that they're younger, right? Do you not? Okay. So let me try again. All right.
But not
This
with
is
this
ignoring
equation.
the fact that some young people could have $1 million.
No. It isn't. It totally is not. You guys have got to get over. Probability does not mean nobody does that. So let me try this one. Let me go ahead and get in trouble in a million different ways. All right. We see somebody in the parking lot, and we don't know if it's a man or a woman, right? Can't tell. They're kind of far away. You with me? Can't tell you. We don't know how they identify. We don't know any of that stuff. So this was, but my friend says, oh, I saw that person get off a Harley Davidson motorcycle. Now, this is where I get in trouble, and this is really, really kind of silly. None of my answer means no women ride Harley Davidson motorcycle, but hasn't the probability that it's a man gone up? Isn't that true?
Yeah.
Yes. Now, I am definitely not saying I had this young lady who wanted to kick my ass because she rode a Harley Davidson. I'm like, I never said that no women. So this is the misunderstanding about low and high probabilities. Low and high probabilities doesn't mean that it will never happen or that it will definitely happen, right? And most of us don't think that way, right? We see the vaccine is given. They tell you that there's a chance that it will keep you from getting infected. And then some people get infected, and then idiots go on the internet saying, look, I told you the vaccine is shit. And then I'm like, no, the probability of getting infected went way down. That does not mean nobody who gets vaccinated can get infected. Are you guys with me? So this basic misunderstanding of percentages and probability leads to bigger misunderstandings that lead to people getting hurt. So that's why I like that you're taking this class. You don't have to trust me with anything I say, by the way. You can always double check. I'm not here to tell you how to think or anything, but there's some basic facts that we need to know. All right, so everybody, is that better? I don't know. I gotta come up with some better examples. Okay, all right. I mean, given that it's 4
That's
p.m.
just different. That's different than the card equation, because the card equation, oh, I see. You're given that it's a king.
No, given that it's a club, this one did not change. So these are independent. King and clubs would be independent, because does a king give a shit that clubs happened? Nope. The probability of kings stayed exactly the same. Now, let me do this. Let's do this. All right. How many of these have faces on them? How many of these cards have faces on them?
3.
3.
3 of them, right? So how many total cards have faces on them? 3 times
4.
12.
12.
Oh,
So there's 12 face cards, yes? So what is the probability? Geez, Jeff, what language? Is this hieroglyphics? All right, there we go. 12 face cards. What's the probability I get a king given that it's a face card? So what's going to go on the bottom now if I know it's a face card?
12.
12. Out of those 12 face cards, how many are kings?
4.
4.
Yeah.
Okay. Which is what percent? 4/12 is 1/3 is 33.33. Is that cool? Just to round it off. Did that change the probability at all? Did the probability change at all?
Yes.
I really want you to understand. Get this. Isn't this a question about the probability of a king getting a king? Of course it is, because that's probability of a king, Jeff. What's your problem? So is this. This is a question about the probability of a king. I'm just given more information. So did the probability of getting a king change if I knew this?
Yes.
Yeah.
Totally. So wouldn't you say that king and face card
Are dependent.
are dependent? Now the mistake people make is this means the probability changed. It doesn't mean the probability became 0. It doesn't mean the probability became 100%. It just means the probability changed. That's the mistake people make with the Harley Davidson example. It doesn't mean that no women ride Harley Davidsons. That's not what that means. It means the probability that that person's a woman went down. Is it still possible they're a woman? Of course. Is that pretty cool now? All right, so if I ask you a question about whether two things are independent or not, you cannot write a paragraph and get the answer correct. You have to compare numbers. It's a purely mathematical idea. Maybe? Maybe. All right, there will be an example of this on the sheet that we do. All right, so this is the idea. So these are dependent and these would be independent. Just because the probability doesn't change once I know one of them happened. Okay, I like it. I was about to say, when things go back to normal, I think even now, does anybody agree at certain times of the day, if you're in San Diego in a certain area and it's a certain time, you might just not try to hit the road. You'll just sit back down and say, we might as well stay here. You guys, so isn't the probability you get somewhere quickly dependent on the time of day it is in San Diego? Shit, yeah, because your probability changes. And that's an example of the amount that it's hardwired into our brain. Probabilities are difficult because they have not been hardwired into our brain. The only amount of hardwiring in our brain is, sun going down. If I go that way, saber-toothed tiger. If I go that way, less saber-toothed tigers. I'm going to go that way. You guys, that's the extent of probability in our brains so that we can evolve and get to this point. All right. So there's another, let's do this since we're talking about this. There's one formula we haven't done yet. We got the or, we got the given. So of course, what's still missing?
The and.
And, okay, so let me do this two different ways. All right. I'm gonna do this in a very morbid way. Okay, not morbid, I guess. I don't know. It is kind of morbid. We're talking about death. So do you guys know the space shuttle has exploded, or it's no longer a thing anymore? Unfortunately, they retired the program, but the space shuttle, when it was running, do you guys know the space shuttle? Does anyone remember the space shuttle? Do you guys know it blew up twice? Blew up twice.
Yeah.
Yes. All right. First time it blew up was in '86, maybe, and it went up and blew up. And the second time it blew up was when it was trying to come back to Earth, and the heat tiles had come off in space, and so it blew up across Texas and all that kind of stuff. Does anyone know why it blew up the first time? Back in '86, when Jeff was in English class, and they came over the loudspeaker and they told us it blew up, and I remember that specifically because I started to cry. I was such a big space shuttle geek. We normally, it was down in Florida, we would normally go out and watch it take off. And for some reason, we didn't go that one day. Thank God. Can't imagine what would have happened to me if I saw it.
There was an O-ring.
Oh, look at you.
on the booster rocket.
Yes. And what's an
froze.
O-ring? Do you know what an O-ring is?
It's some part of the booster rocket that holds things in place, but I don't know more than that.
Basically like a valve.
Okay.
That keeps the fuel flowing in one direction. So would it be a bad thing if it failed?
Yes.
Yes.
Yeah, because if the fuel's going in the wrong direction, something's going to explode, like what happened in 1986. So why would you want more than one of these things?
Redundancy,
Redundancy. What does that mean for everybody?
like backup safety
Good.
stuff.
So for one example I give is if you had a final exam at 7 a.m. the next day, does anyone ever do this in the situations? You set more than one alarm clock kind of thing? Does anyone ever do that?
Yeah.
Okay, me too. I do the same thing. I'll set multiple things. If I'm in a hotel and I'm at a conference, I'm supposed to do a presentation at 7 a.m. I'm like, hey, can you wake me up here? Let me set my clock. Let me set their stupid little alarm clock thing. I got 3 things now, you know. So the probability that I will not get woken up gets further and further lower as I do more and more things, right? That only makes sense. Okay. So let's say that, let's just pretend this is not true, but let's say that there's a 1% chance that these will fail, right? So bad things happen if O-ring 1 and O-ring 2 fail, correct? That's when bad things will happen, yes? So thankfully, we don't do what we do with OR. If we do what we did with OR, we would add these and the probability would go up. That would be exactly the wrong thing, correct? We don't want the chances of blowing up to go up when I put some more stuff in here. No, we want it to go down. So what kind of makes sense here? 1% of the time, let's say, okay, this thing is going to fail 1% of the time. Of those times, how often will this one fail? 1%. 1% of the times that this fails, so 1% of 1% is how often they both would be expected to fail. How do you do 1% of 1%?
0.1 times 0.1.
Almost. That's 10% of 10%.
0.01 times
0.01 times 0.01.
Yeah. And isn't this just this probability times that probability? Yes? So in normal conditions, the probability that they both fail comes out to be 0.0001. So 1 out of 100 chance for one of them, but this will be a 1 out of 1,000 chance. No, Jeff, you can do better than that.
10,000.
Can we go back to king and face card and why?
Not at the moment. Wait, unless it directly applies to what's happening here. So what's your question? Does it apply to what we're doing right now? Hello?
No, this is an and. It's different than the line.
This is an and, exactly. So I want to stick on this
dependent.
idea. Yeah. You got to stick on this idea. Now, the other thing, I think this has something to do with what you're asking. Why then did this not work? Because it was icy, it was cold. And in those conditions, these fail. These get harder, they can't do their job correctly. Yes? Okay, I like it. So to be honest, they weren't really independent. Their probabilities, all right, let's get a little too deep into it.
So that time that it failed, that was the 1 out of 10,000 time.
Here's the thing though, under normal operations, now listen to me, couple things. 1% is way higher than the actual probability of failure in normal conditions. You with me? I just made it 1% to make our math easier. Is that all right?
Yeah, because 1 out of 10,000 is still really high.
Yeah, exactly. Yeah, but it's definitely a lot lower than if you only had one of these things, correct? So if they really were 1 out of 100 chance, wouldn't we put like 8 of these suckers at least in here, right? Does that make more sense for you? Is that like where you're going?
Yeah.
Yeah. So if the probability is really kind of relatively high, then I want to put many, many. So if I have a shitty lock on my door and I live in a bad neighborhood and the only kind of locks I can get are shitty, am I not going to put like 10 of those bad boys on there? So shitty plus shitty plus shitty plus shitty equals not so shitty, hopefully, right? No? Okay. So the main thing I want you to get from this is, and basically means multiply. Now, there's more to the story. Does everybody see and means multiply? Because that's what we just did. We multiplied. What does or mean? What's in the formula for or? Or basically means to do what? What operation?
Addition.
Addition. I love it. And I say basically because I sometimes have to subtract a little bit off, correct? For or. All right. So let's look at this thing. I have another example that's kind of silly, so I'm just not going to do it. We're just going right into the algebra. Here's the formula for given. I don't know if anybody thought about this earlier, but can't you just solve that for and? How would you solve that for the probability of A and B?
Divide by the probability of B.
It already is
Or
divided by the
multiply.
probability. Multiply, there we go. So then I would get probability of A and B equals probability of B times probability of A given B. Let me stop for a minute.
That is the and formula.
That's the and formula. And what did we notice? Isn't there a times here? Isn't that cool? Just like we kind of came up with that made sense in the other example about and. Okay, maybe, no. Here's something a little weird about this formula. So here's one main form. Now watch. Can somebody tell me what's the probability of B given A? What would that be? It's probably B given A.
Probability of A and B. Divide by A. Probability A.
Kick ass. So isn't the probability of A and B also equal to the probability of A times this? What's up with you, dude? I gotta tighten you up. Poor little thing. All right. It's gonna drive me crazy. You guys, so that's a little confusing. I don't know. You have two different ways you could do this. All right. So let me give you some concrete examples. No more space shuttles exploding or just letters. Let's do some concrete examples, right? It's like, please, dear God, Jeff, yes. Now let me not do cards in case somebody's not good with cards and you just didn't speak up. Is everybody ready? I'm going to erase this. You guys ready? See if anybody screams out. All right. So let's go to good old standard in a bag, but let's put some, what do you got, Jeff? Let's put some M&Ms. We got 4 packets of M&Ms. We got 5 gummy bear packets. And we got 2, what do you like? 2, I can't think of anything.
Sour Patch Kids.
Sure, Sour Patch Kids. Okay. Speak. All right. So we'll say M&Ms are M, gummies are G, and Sour Patch Kids are S. That's great. Let me make it P for patch because my S's look like 5s. All right. Now, if I pick 2 candies from this bag, and I've got to tell you how I do it with, Jeff, what are you, Old English? With replacement. What does that mean? I pick something and then I drop it back in, right? And the next guy's like, what the hell, man? Double dip. All right. So I pick something and I drop it back in, and then I pick the next thing. What's the probability that I pick M&M packet and then gummy bears? All right, let's see how this is going to work.
It's the same.
What do you mean? Okay? So here's the formula. Here's the formula, right? So this would be the probability of M&Ms times the probability of gummy, given that I picked an M&M. Is everybody with what I've just done? Because there's the formula. That's how AND works. And by the way, here's an example of a situation that I need to use a formula because I don't have all of these possibilities splayed out for me. I can't count them. I don't know if you guys are with me. I can't just count the answers because I don't have every way to do this. Is it pretty cool with what I did here, just based on the formula? Yes? What's probably get an M&M? Packet of M&Ms. M&Ms. Anybody? Yes?
Out of 11?
What was the top? Sorry?
4?
4. Okay, so 4 M&Ms out of 11 things, yes? And then I drop that back in. So does the probability of gummy bear change because I picked M&Ms first? So does this probability of gummy bear change at all? It would have changed if I picked the M&Ms and did what with it?
Didn't
Ate 'em.
put back.
Held it.
Ate them. Because then what would have changed?
There's no M&Ms.
No,
The
there
number.
would have been 3 left. There would have been
Oh, well,
one
yeah.
less thing in there. But that's not what happened. I said with replacement. I throw it back in. So what's probably get gummy bears now? Well, it's still 5 out of 11. And then whatever the hell that is. Let's see. 16.165. I don't know. I could be really wrong, so don't hesitate to correct me. I probably went the wrong way in my head. Let me think. Why is this taking so long? Is anybody do that for me? No.
0.1653.
Holy shit. That's pretty good. No? Come on, it's my one skill. It's my one skill. No? Oh, you're like, I'm not impressed, Jeff. You didn't get to 3. All right, you're right. You're right. So, all right.
Just to clarify, this formula is for an actual example in which you picked out an M and a G, not just before you picked.
All right, I'm not, what do you mean? Sorry.
So the formula, it says M and G. There's no P for, oh wait, the P is not, is the P for probability or the P for Sour Patch Kids?
Oh, I see. All right. Let's make Sour Patch Kids K. All right, I'm sorry. So this is the probability that I pick M&Ms and then gummy bears because I'm picking 2 candies, right? So here's my.
So you're looking specifically for M&Ms and gummy bears.
Yes, exactly. Yes. So I get M&Ms first, and then so times gummy bears. So it's like I get gummy bears 5 out of 11 times, and of those times I get M&Ms 4 out of 11 times. So it's just like the space shuttle example, right? But just remember, and is basically multiply. Because what do you guys know what happens? Now, normally when you multiply 2 numbers, does it get bigger or smaller? What's 2 times 7? 14. Okay, so normally they get bigger. What happens when you multiply 2 numbers that are less than 1? What's 0.5 times 0.5?
They get smaller.
It's smaller, it's 0.25. So, and should be smaller. And that's exactly what multiplying 2 numbers less than 1 becomes, smaller, right? And is more restrictive. It should be smaller, should be less likely to do an and thing. Okay, I don't know how you guys feel. Okay, so here, you guys try this one. And then we'll do, let's see. Let's probably get Sour Patch Kids and then M&Ms. So do that real quick while I turn my AC on. So I always do like a little hangman game. Something and something else. So I got two things. What goes here? It's probability of getting
2 out of 11.
Yeah, 2 out of 11. I throw that back in. Right? So what's probably now that I get M&Ms?
4 out of 11.
4 out of 11. Right. And then whatever the hell that is. 31 and a 15.
0.0661.
Oh man. All right. It's almost there. So this would be like a 16.5% chance almost to get M&Ms and then a gummy bears. And this would be about a 6.61% chance to get Sour Patch Kids and then M&Ms. Now, obviously, with candy, I'm probably not going to toss back in the first thing I got. I'm probably going to eat that bad boy. Right? Right. Unless it's, for me, it's black licorice. I don't like black licorice. So I'll throw that back in. So watch this. What if I were to do, let's see, where can I put this? Put this in a different color. What if I were to do the same problems, but I do it without replacement? Meaning I eat the first thing I get. So what's the probability I get M&Ms and then gummy bears now? Well, what happens? So the probably M&Ms, nothing's happened yet. I haven't picked anything. But if I pick an M&M, what's the probability of that happening?
4 out of 11.
4 out of 11. Then I eat it. Oh, so now what's the probability I get gummy bears?
5 out of
5 out of 10.
5 out of 10. Exactly. There's one less thing.
Yes. Okay.
I like it. There's 4 packets of M&Ms, packets of gummy bears, packets of Sour Patch. So I pick 1 packet of M&Ms, eat it. So now there's one less. Why didn't the top go down from 5 to 4? Because it wasn't gummy bears I picked. It was M&Ms. So of course there's still all 5. I can't do that with that in my hand. All 5 gummy bears. Is everybody with this so far?
Mm-hmm.
Or means add, basically. And means multiply, basically. So why do I say that? Because the second guy or any other ones, I could pick 15 things out of here. Well, maybe not 15. But yeah, I could just have a big list of all of these things multiplying. You guys understand? M, G, K, blah, blah. I can just keep going. And you would just keep multiplying and multiplying and multiplying. Because and basically means multiply. What about, let me do one different than this. What about probably getting Sour Patch Kids and then another Sour Patch Kids? Let's probably get the first Sour Patch Kid.
2 out of 11.
Good, 2 out of 11. I eat that. Let's probably get then another Sour Patch Kid.
1 out of 10.
1 out of 10. Good. Now the top changes because I did pick a kid, ate it. That sounds terrible, Jeff. These things happen. I picked a Sour Patch Kids and I ate it. And then this is going to be 1 out of 10. What is that? 0.01. I don't even know. I would be guessing after that.
0.0181 or 82.
0.0182. Okay. So like a 1.82% chance. Of course, it's a very small chance because that's what they have the least of. There's only 2 of those. So it's probably I get both of them. That should be a pretty small probability, right? That kind of jives with what we know should happen. Okay. All right. Let's see.
You want your answers in decimals or in percentages?
I need them in 4-place decimals, and then you can make a percentage if you want to.
Okay.
Yeah, I like it. And please, dear God, I must see this work. Don't just put this number down out of nowhere. I have no idea where it came from. If you make a mistake, I'm going to take as many points off because I don't know what you did. Okay. All right.
I have a question.
Yes.
How is given different than and?
Oh, okay. Well, so different. Do you notice how each and the bottom is the total of everything, correct?
Yeah.
The given is the only probability where the bottom isn't the total, because I've been given information. I can throw people out. So if I said, let me see. If I said, what's the probability I get an M&M? So I pick one thing out of here. Let's probably get an M&M given that it was not gummy. Let's see if you guys can get this neat problem here. So given that it's not a gummy I picked, what's the probability it's an M&M's? So how many things am I talking about now if I know it's not a gummy bear package?
6 things total.
Is everybody with me on that? Is everybody with whoever is speaking? I think it was Ann.
Mhm.
If it's not one of these, then it must be, there's 6 things it could be. Out of those 6 things, how many match what we're looking for?
4.
4. Right? What's the probability of M&M normally? 4 out of 11. What did this become since it was a given? 4 out of 6. Because I'm given information, the number of things it could be is less. Right? So it's sort of like a detective thing, right? If you're trying to find suspects, what are you going to first do? If anybody in the city could have killed this person, what are you going to first do? You're going to try to do what? Has anybody watched enough of these shows? What's the first thing you do?
Figure out who didn't do it?
Sure, yeah, figure out who didn't do it. But you're going to do things, all right, like who could have been in that area or who could not have been in that area? Who could not, yeah, you can eliminate. And what are you doing if you're eliminating suspects? You are decreasing the denominator in your probabilities. You're increasing the probability of everybody who's left, right? Okay. All right, so you guys, let's take a break and then we'll do the practice for probability and then we'll see what time it is. Is that cool, everybody?
Yep.
So let's see, what time is it currently? 2:30. So let's come back at 2:40. What do you guys think? Is that all right? That's not enough time, is it? Let's come back at 2:45. 2:45.
Right, time for coffee. Thank you.
Sure.
I had a quick question on my 2.2 homework.
Yeah.
So for that one, obviously for the relative frequency, if you divide 14 into 65, it's going to give you a decimal that kind of goes on forever. So I rounded to the 3rd decimal place. And like estimate rounded up. But then at the end, I added it and it gave me 0.9999999. So like, is that okay? Or how do we do that? Because I know it's supposed to equal to 1.
No, you're fine. I told you, if you do any rounding at all, it is very likely that it's going to add up to be not quite 1. It's going to be a little more than 1, a little less than 1. Sometimes it'll come out to be exactly 1 if you just happen to round up just as much as you rounded down. But with natural fluctuations in numbers, you could end up rounding up a couple more times than you rounded down. So it's going to be higher than 1, like 1.003 or something. Does that make sense?
Yep. I just want to make sure for the chapter 2 quiz, if it didn't equal perfectly 1, that was okay.
Yeah, that's a really good question. In general, it's got to be really close to 1, but it doesn't have to be 1. If it's not 1, it doesn't mean things aren't real or not valid or something. Very good.
Okay. And then what does the 1 actually mean? I know that the total number, once you have frequency, should equal to the total number or amount of values or data points in the sample. What does the number 1 mean?
Well, let's answer that the opposite. What if you would have gotten 0.9 instead of 1? Isn't that pretty far away from 1?
Yeah.
That means you're missing 10%. So what is, I basically just gave it away, but
it means 100%.
That means you left out you must have left out some of the data, right? So why does it have to be 1? Because that would mean that you've collected all of the possible data. Another thing I've seen people do, which is really smart, is if you keep them in fractional form, don't they add up to be 65 out of 65?
Yes.
Which means you've accounted for all of 65 salesmen, which means you've done it correctly. You didn't leave anybody out.
Okay, so the 1 doesn't mean anything. It just means 100% pretty much.
Well, yeah, it means 100%.
Okay.
Yeah. Samantha, I don't know when you asked that question. Oh, I guess it's not too long ago. When do you use each formula? Well, if I ask you what's the probability of B given C, then you use the given formula. If I ask you, I mean, that's really, I don't know what more to say than that. There will be some situations where I have to think, is this an and? Is this a? But I mean, it shouldn't be too. I don't know if that helps you out. I don't know. You got to get in there and try the homework out and see if you find a problem that you're not sure, and then you can ask me specifically. But most of the problems are going to be pretty straightforward about, do they want an or, do they want an and, do they want a given? I'm sorry. So again, it's try the problems out, see if you hit any that are kind of like what you're worried about, and then ask, and then it can tell you in those situations what things mean. Right? It's kind of hard to cover for every possible situation ahead of time.
I have a question from the 3.1 homework. So it's just like I said, I'm writing the formulas for probability based on like baseball players. And the first one is rate the symbols for the probability that a player is not an outfielder.
Oh yeah. Okay.
So how
Yeah,
would you
there's always little tiny things I forget. So it's I think the book, for some stupid reason. So what I use, and what most statisticians use, is this to mean the probability of not A.
Okay.
Yeah. The book uses a symbol which is really, really silly because it uses a little tick like that, like a feet marker, but it's so easy to lose that.
Okay.
So I would much prefer this means not in probability.
Okay.
Yeah.
Thank you.
Well,
Is there also a large tilde that's used for complement?
I mean, the same way this book uses a little prime symbol. Mm-hmm. I've seen different things used in different situations. I can't think right now off the top of my head. Have you seen the tilde used to mean not somewhere? That's more in logic.
Yeah, I was thinking back to a logic class.
Oh yeah. So in logic, they use the tilde to mean the negation of some situation. Yeah.
Okay.
Yeah.
I was just thinking in stats, a bar might be confused for mean, but I don't know.
I know, I'm with you, but that's the standard thing. I've never seen until this book, the prime symbol, which of course in my mind means derivative, but I'd never seen it before until this book. Yeah. And it's unfortunate the bar means something else too.
Okay.
But we don't really run out of symbols. We just have symbols we kind of like for some reason. We just keep using them over. In the first part. Oh, what matters? Okay. So somebody's got a really good question. So the two ways to have the and formula. Jeff just stated. What's really important, if that's A, then it's got to be times probably B given A. So probability of A and probability of B both have to show up. So if instead we put probability of B, then this has got to be probability of A given B. Do you see that? So like when we did M&Ms, this has to be fundamentally about M&Ms. When we did gummy bears, that's why there's a 5 there. This is fundamentally about gummy bears. They both have to get a turn. Okay.
So would the second formula be probability of B and A then? Since there's
Now listen, if I said Matthew and Billy come with me, or I said Billy and Matthew come with me, are those two different things?
no.
No. So A and B is the same as B and A.
So how would you know when to switch the formulas around?
The funny thing is
Either or, you know what I mean?
I know what you mean. I know exactly what you mean. The funny thing is the letters themselves really don't matter. They're like X and Y. Why are they X and Y? Just because. Could they be T and V? They totally could be. Could those be W and an L all day long? So the only time it's really going to be an issue is, man, let me ask you this. If they told me that the probability of A is 0.1, and they told me the probability of A given B is 0.3, and they told me the probability of B given A is 0.5, how would you figure out the probability of A and B?
I would use the probability A times the probability of B given A.
Good. You couldn't use this formula because you don't know this.
Right. Okay.
Okay.
That makes sense.
You're welcome. All right. So there's actually two. Oof, so many ideas. There's two more ideas I need to talk about, and then we'll do this practice thing. Let me see if you guys, all right. Let's see, what order do I want to do this in? Okay, we got it. Am I blurry? A little blurry. Why is that there? I don't know, Jeff. No! Okay. All right. So real quick, let me see if I can do this real quick. Let's just make a really boring problem real quick. I have 4 blue marbles, 6 red marbles, 11 green marbles, and 3 white marbles. Okay. And I pick 5 marbles. Yeah. Without replacement. What is the probability that I pick blue and then a green and then a red and then another green? Yeah, baby. Calm down, Jeff.
That's only 4.
Sorry?
That's only 4.
Oh, shit. Thank you. And then I was all excited. And then I can't count. Fortunately, you guys have figured it out now. And then another blue. It really doesn't matter, to be honest. Just want to make this point real quick.
It has to be in order?
What do you mean? No. Oh, it's interesting. I'm being very specific about how this is being picked, because otherwise this would be a very hard problem. I want you guys to understand. If I said I pick 5 marbles and I get a couple of blue, a red, and a couple greens, does anyone understand why that would be really would take you longer to do? Because it could be in any order at all, right? So here I'm being very specific. So it's only one calculation we have to do. If I just said a couple blues, a couple greens, and a red, well, did the red come first? Does it come second? Does it come last? Did the 2 blues come first? Did one blue come first and then last, or in the middle, or the green? And where's the green? And what the hell? What's the other one doing? Holy shit, that would be a lot of calculations. We have to do all of them and add them all up. So that's going to be chapter 4. We'll develop a shortcut for that, thank God. Okay. So that's why I'm being very specific. So that's a good question. So I got 5 things now, thankfully, because Jordan kept me straight. Without replace, what's probably the first one is blue. What's probably the first one is blue?
4.
4 out of
24.
24. I like it.
Did I do that right?
Sorry?
Sorry, I didn't know if I calculated it right.
Yeah, you got it. Right, and this is without replacement, right? So I feed that to my little brother. What's probably the next one is green then?
4 out of 23.
11.
11
11
11 out of 23. So I like the bottom there. Good. I lost the marble. Right? I lost many marbles. Lost most of my marbles. So now it's probably the next one is red.
6 out of 22.
22. Of course, what's going to happen to the bottom all the way through is just going to keep going down by 1, right?
Mm-hmm.
Now notice somebody always puts a 19, or I'm sorry, a 20 here. Why do you think somebody would put 20 here?
Because they took the whole 4.
Yeah, but we don't pick all 4 blues, do we? This represents the probability of 1 marble. So I've lost 1 marble. I lost another marble. Now let's probably get, where am I at? Blue, green, red. Let's probably get another green. Uh-oh.
10 out of 21.
Good. 10, because I already picked a green that's gone. Out of 21, I lost a marble. And then, of course, another blue.
Jeff, you're losing your marbles.
Oh, dude, like I said,
Green.
I'm
I've
just
lost
happy
my
I got a
marbles.
couple still knocking around. Sorry?
3 out of 20.
3 out of 20. Is everybody cool with that? I had 4. I picked 1 here. So, of course, I've got 3 left back here when I want another one. Right? Okay. And then you just multiply all this shit together. I don't know what that is. I actually don't care. Let's see, 122, 1/2, 146, 1/2, 1/7. So 0.014 roughly. I probably did that. What is it? 0.0015.
00155.
Oh,
Yeah.
what is it? 00?
155.
That's pretty good. That's not bad. That's pretty good. Holy shit, guys. I did all this shit. I'm sorry. It's my one skill. It's my one skill. I gotta show you. All right. Is that okay? I just wanted to show you, you have 5 spots because there are 5 things, and you fill in the probabilities and you multiply as you go because it's and. And basically means multiply. Now, would you say our sample is, would you say our population, this is a population, would you say that it's very big? Would you say this population of marbles is big?
No.
Hell no, right? Compared to the population of America, compared to the population of the world, dude, right? So, what if I had a problem about all Americans, let's say? Let's say that 11% of Americans enjoy Brussels sprouts. Is that how you spell it? I don't even know. It's supposed to be capital B because it's from Brussels. I think. I don't know. I'm bad with my vegetable history, so excuse me. How many Americans are there?
A grip.
Huh?
A lot.
A lot. It's not like you said a crew. We got a crew together.
I said a grip.
A grip. All right, I have no idea what that means. So what if I pick 5 Americans? And I want to know the probability that the first one enjoys Brussels sprouts and the last 4 don't. First one. There we go, Jeff. So we got 5 Americans. 5 Americans. The mistake I see a lot of people make is they'll do this. Do not write this. That's so wrong. What is really wrong about that? How many Americans? Huh?
Full size.
We just talk about 11%.
I'm saying this person is saying there's only 100 people in America.
There's no sample size.
Well, yeah, the sample size is 5, so it's 1 out of 5, not 1 out of 100.
No, guys. No. Sample size is 340 million, whatever the hell America is. Right? Where these
Oh, you
5
said
people?
pick 5.
Yeah.
Pick 5
So,
Americans.
Yeah, we're picking from all of America, right? So please understand this. All right, now listen. Stay with me. Remember that 4/24 we did? I think that was for the blue marble on the last problem, right? Remember that?
Mm-hmm.
Remember those days? And then what happens to it if I pick a blue marble? If I want to pick another one, wouldn't it be 3 out of 23? Is everybody with me?
Mm-hmm.
What is 4 divided by 24?
Something.
0.16.
6, 7.
And what is 3 divided by 23? I don't know what that one is.
0.1304.
1304? Is that right? Would you say now? Did this change by a lot? No, but did this change? I want you to understand a 3% change, over a 3% change is huge. So when my population is small, which it definitely was here, this is small, then I must show the fractions changing. I want you to stay with me. I have to show each of the fractions and how they change. Now, watch this. What if the population had instead been, let's just do 100,000. And I pick 1, wouldn't this be 3 out of 999,999, right?
Mm-hmm.
4 divided by 100,000 is obviously 1, 2, 3, 4, 5, I think.
Mm-hmm.
What is 3 divided by 99,999? Somebody tell me.
0.00003.
No, come on. It's not. No.
It's 4 zeros.
It stops at 3?
Yeah.
It just stops at, all right.
Well, that's what I got. Sorry, I'm using my phone.
Oh, okay.
So I could be wrong.
I might have put too many zeros in the first one. Oh, I see. The next thing is way off. So you're basically right. You're right. My bad. And this one actually has 1 too many zeros.
It's just 1 0. Yeah. 1 less.
All right. Now, did that change by a lot? Did that change by a lot?
No.
It changed by 0.00001, right?
Mm-hmm.
All right. So the bigger your population is, the less change there will be in your fractions if they go down by 1 like this. Stay with me.
So that's why they use 4 decks in Vegas for blackjack. So it's harder to count.
Sort of. Now, there's a lot of reasons. Well, it's a very simple reason they do that. It makes it hard to count. So what I'm trying to say here is, when your population is large, you do not have to use fractions. You don't have to change it as you go because it's barely going to change. So what's the probability that the first one likes Brussels sprouts? What's the probability the first one likes Brussels sprouts? You know it. I told you what it was. What's the probability somebody likes Brussels sprouts in America?
11%.
11%. What's probably somebody does not like it? I want the last 4 to not like it.
89%.
Because if you made the fractions, it would be out of 340 million, whatever the shit, and then it would go down to 339, 999, I mean, and it would basically not change from 0.89. It'd be like 0.89, and then it becomes 0.8899999997, which is basically freaking 0.89. I don't know if you guys are with me. This is a beautiful shortcut we can do when our population is really big, right? I don't have to do fractions when the population is really big. If I give you a percentage of a large group, you can just use the percentages directly. And then can somebody help me out here? What's this?
6902.
What is it?
6902.
6902 or is it 069?
I got 0.069.
Yeah. Sweet.
Yeah, 69.
Okay, whatever gets you going. Now. Let's see. Let's look at this. I just activated this. Let me show you on Canvas. We're going to do this together. Whew, somebody else tired. All right, here it is. So probability worksheet, practice quiz. So there's two sides to this thing. One side we're going to do in class, and we'll find out if my Canvas connection does. Let's try to refresh this. Let's see what happens. That's exciting. Is anyone else able to access that? That'll suck if you're not able to. Hello? Are you guys trying to access that? Anybody able to go into Canvas?
Yeah, I got it.
You got it? Okay. It doesn't want to show me. It's like, whatever, dude. All right, so let me open that a different way. Hold on.
Mine's doing the same thing yours is doing.
Okay. Let's see. Probability, where are you? There it is. All right, so now I can do it this way instead. All right, guys. So let's kind of go through this. I'm going to let you do a couple of these and then I'll catch up to you, that kind of thing. You know I'm going to give you a problem like this, right? You know you're going to get a problem with the big table and you're going to do probabilities. And of course, I'm being really, really nice because I'm giving you blank spaces. So you should immediately remember you got to figure out what those blank spaces are. You got to calculate all the totals. So it's all take a minute and kind of fill in these blank spaces. Am I doing this right? Yes, I am. Oh, what is that, Jeff? I think it's that. Is that true? Yes, okay. Yay, Jeff can add. Yeah, it did a little bit. Whoa. Someday we'll find it. I can't quite do Kermit. The rainbow connection. I could do Cleveland. There it is. Oh, Peter, that's nasty. So do the first couple of prompts. These should be pretty quick. So I'm taking one person. It's nothing freaky yet. Just one person is being selected. All right. So what is the probability that we pick somebody who attends Grossmont College from this group?
1 out of 126.
So there's only one chance to get a Grossmont student?
126 out of 176.
Oh, I'm sorry. Is that what you said? I might have misheard. So 126 chances to get a Grossmont student out of 176 students. I like it. Is there any questions about that one? And on the quiz itself, I don't think I said it back here, did I? Oh, here, I did say it here. I will say this. Round decimal answers to 4 places. So that your answers must be 4-place decimal. So somebody help me out. What does that come out to be?
Thousand.
0.7159.
7159. Yeah. Right, when you divide that, that's what you get. I like it. All right. And by the way, this might not occur to anybody, but each of these problems is distinct. Each of these problems resets. They don't build on each other. So what's the probability from this whole group that I pick a business major?
92 out of 176.
There we go. One big thing that you should be concerned about, never leave the answer to a probability question bigger than 1 or negative, right? You can't have a negative probability. That's weird. You can't have a probability more than 1, right? So what is 92 divided by 176?
.5227.
Yes, and of course you can make that into a percentage if you want to. It's totally up to you. I've heard that most humans enjoy that. So what about, is everybody cool so far? Anything weird yet? Okay. So this one is an OR problem. I'm being very nice here and making a big old OR. Computer science or goes to Grossmont. So there's a few different ways you could do this one. If you do, well, what's going to be on the bottom for sure?
176.
Good, because I don't know anything about the person. It could be anybody. Has somebody figured out what goes on top?
73 plus 73 over 176 plus 126 over 176.
All right, if you do this, what's not quite right yet?
Minus 62.
Minus 62.
Good. If you add these people to these people, you've added these people twice. So this is kind of like more the book, the formula way to do it, right? Nothing wrong with that, by the way. I did not mean to say that as a pejorative. I think it's one of the first times I've ever used that word. Ooh, pejorative. All right. The slightly better way to do this is to say, okay, there's 126 Grossmont students, right? How many computer science people did I not count yet?
11.
So 137, which is what you get if you do the top of that. You guys with me?
Mm-hmm.
So when I have everything I need to count, I do not need to use any formula at all. I do anything I can do to count what I need. That's all I need. But you could use the formula, but very often it makes it harder than it needs to be. And then whatever the hell that is.
0.7784.
Cool. Ciao. Like it. By the way, real quick. We haven't really, all right, real quick question. A real quick situation. I used to be on the East Coast at a college called Virginia Wesleyan College, and I was in charge of way too much stuff. And I would analyze all this data, and we were trying to figure out why this 1 year students stayed at a higher rate than normal. So what I did is I calculated all these probabilities of, given that they did this, what's the probability they stayed? Given that they did this, what's the probability that they stayed? Given that they did it. So then I could see which thing had the most effect on a student's retention. And as most research now has come out to find is if you're engaged, if you're a member of clubs, if you're otherwise have a position at the college, or if you're involved somehow, then your retention is higher, right? And that's basically what I found. And there was a couple other things I can't remember. This is 16 years ago, almost before some of you guys were born. Yay! Now, just to let you know, I mean, there's obviously reasons we do probabilities, right? So this is getting very in the technical, can you do it? But then there's like, why would we do it? All right, so what about this one? So here's an and problem that everybody tries to make so difficult. Do not use the formula for this, dear God. How many students are math majors and Cuyamaca students?
2.
2
76.
out of 176 there. Don't do formula. Formula's insane. Are you used to hearing a math teacher say that? No, because most of the time we need the formulas. Most of the time there's not really a good other way to do it. But here, probability is based on counting. If I can count, if I'm given enough information to count, I don't need formulas. Would the formula work? Hell yeah, if you did it correctly. But it's really easy to mess it up here, so why do that shit? And what is 2 divided by 176?
0.0114.
I like it. I like it. All right, now here's our first time that what happens in part E. This is the first time that something happens. Certain something.
Bottom number changes.
Good. What's the bottom number become?
73.
Good, because we know they're a computer science majors, so they must be here. So we're only talking about 73 total people, and out of those people, how many are Grossmont students?
62.
Good. Now somebody will give me this answer. How can you tell immediately this answer is wrong? Good Lord, Jeff.
The top number's bigger.
Yeah, it's top heavy, which cannot happen in a fraction that represents a probability because then it's greater than 1. So what that person did was they counted all Grossmont students, but I threw these people out. It's definitely these math people. Ugh, threw them out. Business people threw them out. So I've only got this many Grossmont students left alive. Killed all the others, just killed. All right, sorry. I gotta calm down. I'm getting tired, so I get even worse, weird. I'm tired. And I'm running out of special juice, which might be better. And what is 62 divided by 73?
0.8493.
Are you drinking Rip Fuel, Jeff? Jeff?
What is it? Sorry? Jeff?
Rip Fuel? Like pre-workout?
No, that was just tea. I drink tea.
Okay.
I'm a Georgia boy, so I drink a lot of tea. My blood runs red and brown. Just for the tea. All right. Now, think about this problem, part F. I'm going to say this again. If I ask you, are these 2 events independent, and you start writing a lot of words, you are wrong. Does that mean the answer can have no words? No. The answer is primarily a math thing, though. And I will tell you this, we've already calculated 2 things that I need to answer part F.
It's not independent because it has to be a Grossmont student and a computer science major. It's like pretty obvious, right?
No. Are this event and this event independent? I've got to use the word and because we're communicating in English. So and doesn't always mean the probability and. So are this event?
You can be a computer science major anywhere.
They're not independent.
All right, now listen to me. In this sample, and dependent does not mean it cannot happen with the other thing. Dependent means if I know one of the things, does it change the probability of the other one? So in this case, what's the probability that it's a Grossmont student if I know they're a computer science major? Didn't we calculate that?
Mm-hmm.
What is that?
0.8493.
All right, and what's the probability they're a Grossmont student just without knowing anything about computer science? Just what's probably they're a Grossmont student?
0.7159.
Yeah, it's the very first thing we did. So if I know they're a computer science major, does the probability they're a Grossmont student change?
Yes.
In fact, it went up. So if somebody in this district is a computer science major, I would feel very confident to say, I think they're a Grossmont student.
So this
Right,
is based off the information that we have in the chart, not just in general.
Yeah, just talking about the stuff in the chart.
So
So I gotta be
that's why-
careful. In this
okay.
sample, yeah. I like it. But if it's a representative sample, then I would still feel pretty confident. So are they independent? No, they are dependent because the
Just to be
probability of
clear,
one does not equal the probability of it given the other one.
just to
really
be clear,
yes.
Independent, one factor does not change the other. Dependent it does change the probability of the other one.
Yes.
Would be a simple breakdown.
Yes, and I said that before, but yes, that's exactly right. Yeah. If something happens and the probability of the other thing doesn't change, it makes sense that we would just call those independent, right? If you are independent of somebody else and they do something, do you give a shit? No.
Sometimes.
All right. If then you wouldn't be really independent of them, would you? Are you independent from the person that's in the car next to you? No, because their actions can affect you, right? If you are 3 years old and your mom forgets you in the car, is that a problem? Yes. So that would be dependent. Aren't you dependent on your mother and your father or whatever parental units you have? Aren't you dependent on them when you are 3? Of course.
Yes.
Meaning if that thing did something, it could affect me, right? So independent means I know that one of the things happened, but the other thing doesn't care. But in this case, why are they dependent? Because knowing their computer science major totally changed the probability of their growth spun. It made it go up.
So in the sample, specifically, knowing that there's a higher likelihood that a computer science student goes to Grossmont more than Cuyamaca.
Yes. But in this case, what we're saying is there's a higher likelihood. Yeah, okay. All right, I'm with you. That's fine. Okay, so if I know they're a computer science major, it's more likely they're a Grossmont student. Sure. Is that all right? So do you see how many words did I write in my answer here?
So that's all we have to write to explain why or why not?
Say again, sorry.
Is that what we have to write just to explain why or why not?
This is a beautiful answer, and not just because I gave it. I want you to realize this is the way. So that's what I mean. If you start catching yourself writing a lot of words to a question about independence, right? And I don't mean on the history test, I mean here. Are these things independent? And you start writing a whole paragraph, you are wrong. I can almost guarantee it. Now, it's possible you're just over-explaining exactly what we did here, but more than likely you're going to go off on, well, you could be a Grossmont student and not a... No, you're wrong. You can't. That doesn't answer the question. It's a mathematical idea. All right. I think I made this, probably made this worksheet in 2016, and I was just really tired. I pay so much attention to election stuff.
Can you scroll back up just for 1 second?
Yeah.
1 second. Thank you.
So look
over 73.
Okay.
0.8493. Thank you.
Okay. So we have this haunted house, and we lock these politicians in there, right? If we pick one person from the house, what's the probability that the person is a Democrat, right? So this is pretty straightforward. So you want a lot of problems like this because they should be easy. So what is it? What's the very first thing you should do?
7.
Make a little chart.
You don't have to make a chart. How many total people are there?
21.
21. You always want to figure out the total. So 7 out of 21. So that would be 0.3333. Probably is a Republican.
12 out of 21.
Yeah, 12 out of 21. And then
We're
whatever else.
saying with or without replacement in this case.
How many people am I picking?
Oh, you haven't, we just one.
1. So it doesn't matter if that doesn't make sense.
Okay.
But between questions, it resets always. Does that make sense? Okay, I think that
So
might
unless otherwise specified, it always resets.
Yeah, so these problems, I'm picking 2 people, and then I'm telling you which kind of way I'm picking them, right? But this problem doesn't come off of what happened here. Okay. What is 12 divided by 21? Sorry?
I don't want to live in this house.
Yeah, I'm more scared of the politicians, I think, than the ghosts. What is this, though? 4 out of 7, which is 0.5714.
714.
It's a probability that this person believes in Q.
Oh, God. You keep going places I don't want to go, so stop going there.
Okay, sorry.
That's all right. Q is haunting the minds of many people, so that's the last thing I'll say. Now we're taking 2 people, so I have to tell you how I'm doing that. So at first I'm doing it with replacement. Go ahead and try to do part C. I'll finally shut up for a little bit. I'll go get some more drink.
Just about to double cup it.
Drink. So if I were you, put the 2 little hangman blank spaces down there. What goes in the first spot?
2 out of 21.
Good. 2 out of 21 chance for independent.
And then 12 out of 21, I think.
Because it's with replacement. So nothing changes in between.
D, it resets, right?
Yeah, every question is starting from the original problem. Yeah. What do you guys get? Anybody? Are you waiting for me to do it in my head? I don't want to. I'm tired.
0.05.
5442.
0.
544.
544. Okay.
She rounded.
And then 2 Democrats. So that should be pretty easy, right? Each of them are going to get a 7 out of 21 chance. Everybody good? Any questions on that? All right, now do part E and F. This is without replacement. Same questions, but without replacement. I like this one, though. Think about it. We take somebody out. They're like, oh, thank you. And then we shove them back in the house. No, I don't want you. Get back in there. Oh, yeah. All right. Can somebody shoot me an email and remind me? I think it's there was a worksheet before this and this one that I can post these answers for. If somebody will please shoot me a reminder, I can do that. All right. So what happens on part E here?
0.0571.
No, I need you to take me there. So what do you put here?
2 out of 21.
Good.
And 12 out of 20.
Good. Because along the way, we lost a person. So here we picked an independent, 2 out of 21 chance. We'd let them leave. So now there's 20 people, and there's still 12 out of 20 Republicans. That'll be 0.0571. Yeah, you got it. Now somebody else tell me, how does part F work?
Seven over 21 times 6 over 20.
Is that your, all right, that's all right. As for somebody else, just to make sure that everybody.
I'm sorry, man, I drank too much
that's
coffee.
No worries. So 7 out of 21, so that's for the first guy is a Democrat, or girl, sorry. And then we'd let them leave. And now the top and the bottom are both gonna change because we've lost a person and we lost a Democrat. And what is that? Why am I having trouble thinking? Is that 10%?
0.1, yeah.
Yeah.
And all right, is that okay? Work, answer. Work, answer. So forth, so forth, so forth. If you just write down decimals, even if you get it right, I'm going to take some points off. And if you get it wrong, you're going to lose just about all the points because I don't know what you did. Okay. Did anyone know about this? This is actually a true story here, number 4. Now, to really be honest, the way that they worded the survey can explain some of the responses they got, but not all. So it's maybe not 7%, but there's actually a non-zero percentage of Americans who think that chocolate milk comes from brown cows. So I think when I was 3, there was a commercial on TV that made me think that was true, but I kind of, anyway, eventually understood. So this is a lot like that problem we just did with the Brussels sprouts, right? 7% of all Americans think this. We randomly select 4 Americans. 1, 2, 3, 4. First one thinks this way, while the last 3 are reasonable. What's that? So what goes in this first spot?
0.07.
Good, 0.07. And then what goes in each of these spots?
0.93.
Good. Does anybody not see where 9.3 came from? I like it. If they think that way, it's 7%. So they not think that way, it must be 93%. The rest. Now, real quick, this is kind of silly what I'm about to do, but I'm just going to do it because it's going to help us out later. Couldn't I rewrite this mathematically like this?
Why is it 0.93 and 0.07? Why isn't it just 0.07 times 0.07 times 0.07 times 0.07?
Because I'm not saying I want all 4 of them to think this way.
Oh, sorry, thinks 1. Okay, excuse me.
That's right. Now, somebody had an issue with me writing this. Is it because I didn't write my 3 well? Is everybody cool with the fact that I can do this? Right? What's x times x times x? What's x times x times, yeah, it's x to the 3rd power. So what's 0.93 times 0.93 times 0.93? 0.93 to the 3rd power. And this is 0.07 to the first. So I have 1 thinking that way and 3 that don't. So the exponents are actually counting how many did certain things. Isn't that kind of neat? Maybe not. It'll become really neat in chapter 4, hopefully. And then whatever the hell that is. 87205.
Where's the key on our calculator to do
Oh, the to the button?
Yeah.
It's right under the clear button. It's the up caret. Do you see the clear button?
Yeah, see clear, and then I have like a here.
Up arrow. Yeah, up arrow, that's the to the button. Oh. So if you do 7 up arrow 3, that would be 7 to the 3rd power. All right. So who's got that answer? What is it?
0.0563.
Holy shit, that was close. All right. So about a 5.63% chance that'll happen. Now, get ready for this one, guys. So what's the probability that at least one of them thinks chocolate milk comes from brown cows? Brown chicken.
So 1 or more.
Oh, say again, sorry.
That's 1 or more. think
That's right.
that.
That is true.
So you need to add 4 different cases.
Oh, yeah. Oh, God, we do. Thank God there's a shortcut. So here's what Matthew means. Matthew, tell me what you mean. So what does at least one mean? It could be.
Well, yeah, it could be 1 and 3.
Good.
Or it could be 2 and 2.
Yes.
Or 3 and 1.
Yes.
Or all 4.
All 4. Okay. So I want you to, so probability of at least 1. And this is basically also what, I forgot now. Was it Petrina who said that? Greater than, okay. So this is basically the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. Is everybody cool with that? That's at least one person out of 4. There you go, right? How could one of them think? Couldn't it be the first one that thinks that way? Or the second one, or the third one, or the fourth one? I'd have to add them up. What does or mean with probability again? What does or mean? Add. So I'd have to do the situation where the first one thinks that way, plus, because it's or, the second one could think that way, or the third one, or the fourth one. So what about 2? It could be the first 2, or the last 2, or the middle 2, or the first one and the third one, or the first one and the holy shit, Jeff. Make it stop. Stop even joking about this shit, Jeff. This is all right. So thank God there's a shortcut. Can somebody please tell me what is everything that could happen? What am I missing up there? 4 people could think that way. 3 people could think that way. 2 people could think that way. One person could think that way. What am I missing? What's the only thing I'm missing?
No people.
No people. I love it. So doesn't probability of no people plus probably 1 people plus probably 2 people plus probably 3 people plus what's that got to equal? What do I have to get if I add up all the probabilities? What do I have to get?
You have to get 100.
100% or 1 as a decimal, right? Is that cool?
If we're rounding and we get above 100%, are we still correct?
That's fine. But theoretically, if I don't round at all, it should come out to be 1, right? Stay with me now. Stay with me. This is neat. Does everybody agree that this is what the question is asking for right there? This piece right here, isn't this what the question's asking for?
Yeah.
And I don't know if you guys really understand how much work this would take. This would take a shit ton of work. And I don't know what that is converted to metric. But look what I could do. Look what I could do. If I subtract this, doesn't 1 minus the probability of none equal the frickin' answer? I really want you guys to get this. If all the probabilities added make 1, 1 minus 1 piece is the other chunk. I don't know. What's the opposite of at least 1?
More than?
No.
0.
0?
None. So if I said at least one person liked season 8 of Game of Thrones, how could he show I'm wrong? You'd show me that nobody liked it.
Because that show's fucking brilliant.
Season 8 did, for sure. Part of season 7. That's all right. We won't go into that. That's a whole other thing. So here's the thing. How do opposite probabilities relate to each other? Isn't 1 minus the other one? If the probability it's going to rain today is 5%, what's the probability it's not going to rain?
95%.
95%. Right? 100% minus 5%, or 1 minus 0.05. Is everybody with me?
So could we just do 100% minus the probability of 0? Or would
the probability of 0, there's only one way to do that. That's so much less work. So if the opposite probability of what the question is asking, if the opposite is easier, shit, yeah, I'm going to do that. And then I'm going to do 1 minus the answer I get. So the question directly wants a lot of freaking work done. Well, let me just do 1 minus the probability of none. What is the probability that none of them think this weird ass way? Can we just do that? What's the probability that nobody thinks this weird ass way?
93% to the 4th.
Exactly. 9-3, 9-3, 9-3, 9-3. And what is that?
0.07? Oh, wait, sorry. I'm doing it right.
Yes.
0.7480.
Okay. So then this The right answer. So that is the opposite answer than what this question wants. So then if I do 1 minus it, I get the right answer. Oh shit, you guys doing all right?
So 0.252?
Yep. And when does this work, Jeff? Any damn time that the probability question you're given has more work than the opposite of that, then I'll do the opposite and then do 1 minus that. I really want that to make sense. And when does that most often happen in real life? We get these probability of at least 1 problems all the damn time. So this is the one, probability of at least 1 is 1 minus the probability of none. And the probability of none is normally a pretty easy probability to do.
0.
No. If only 7% of Americans feel this way, the probability that none of them think that way should be pretty high. In fact, we calculate it to be 0.7480. Again, we got 4 people, not just 1. So if none of the people think that way, they all think that's false, so that each of them is 0.93, right? None of them think chocolate milk comes from brown cows. So they're all 0.93. So there's almost a 75% chance that any group of 4 people won't believe that craziness, which is still 25% chance that any group of 4 people will. Somebody will. That's like, holy shit, that's a bit much. So there's a 25.2% chance that at least 1 person out of any group of 4 will believe this. Woo! All right, last one. And this is a lot like a lot of the problems in the homework, this part C. Ooh, you're gonna like it. You're gonna love it. Shut up, Jeff. So let me call the probability somebody thinks chocolate milk comes from brown cows. Let's call that probability of C for chocolate. Is that all right? So probably somebody thinks chocolate milk comes from brown cows is 7%, correct?
Mm-hmm.
Now, I tell you that this the probability that Americans think chocolate milk comes from brown cows and that Brussels sprouts, here I am shitting on Brussels sprouts again, I'm sorry if you like Brussels sprouts, are the best vegetable. Well, how would I write? Can you come up with a way to write that? They think that chocolate milk comes from brown cows. That's C. I already established that C. And just give me a letter for Brussels sprouts.
B.
Sorry? Yeah, let's use B. I like it. That's a good idea. That is 0.04, correct? Now, what is the question asking you for? So that's the information I gave you. The question is asking, find the probability that American likes Brussels sprouts. Can you write the formula for what I'm asking given the symbols we chose?
Mm-hmm.
Probably American likes Brussels sprouts given that they think chocolate milk came from my house.
So B.
Yes?
Bar C.
Bar C, I like it. B given C. Now here's why this is so important. Because now that you've got everything identified, what's the formula for B given C? Go ahead and you could argue that I didn't give it to you, but I did, because who cares about A and B? They're just letters.
Probability of C and B.
All right, probably of B and C.
Divide by probability C.
Probably what's on the bottom?
C.
C, good. Does anyone?
What's the difference between B line C and then B and C?
All right, B line C is given, right? So that's when I'm given information.
Okay.
B and C is, I don't know shit. I'm just curious what's probably that they're both B and they are C. Right?
So assuming that they think chocolate milk comes from brown cows, what's
the probability that they like Brussels sprouts? Exactly.
Okay.
Given that we know this person thinks this insane thing, What's the probability that they also like this insane food? Sorry if you like Brussels sprouts. It's fine. Do we know these things? Do I know this? Here's my collection of things I know.
0.04.
Yeah, it's 0.04, right? And do we know this?
0.07.
0.07.
Five seven one four.
Yeah.
0.5714.
That is an example of a problem that we have to use the formulas for, and you must identify the situations with the letter. Why? Because if you don't, how in the world are you going to use the formula? You don't know what goes where. You don't know what means what. There are several problems in the book. Well, there's two at least that I can remember where this is going to be really important. So they're actually going to give you what the letters mean. You just have to collect what they each are numerically. All right, well, you'll find out when you get into homework. Okay. I think that's enough for today. I mean, we've done a lot of stuff. There's some stuff you still got to let sink in. I will post this and the other thing if somebody reminded me. Yeah. Any questions about?
Oh, this all makes sense.
Well, that would be amazing if all of you think this is only so over 50% of brown channel milkers. I like that. Brown cow milkers, like Brussels sprouts. So no, what this is saying is, what was this? Yeah. So out of the people who think brown chocolate milk comes from brown cows, 57% also like Brussels sprouts. I really hope you understand that the 4% thing I just made up, right? I didn't look that up. I don't think that's anywhere. I think anyone's done that study. I think most of us should be happy they didn't spend money on a Brussels sprout study. I don't know. If you don't have any questions, you're free to go. Otherwise, let me know what your questions might be.
I have some questions about chapter 2 for you when everyone's done. Just about box plot construction.
Nobody's. Oh, good.
My question is really brief. It's not really about homework or anything, but I emailed you before the semester started, before the course started, about I won't be here for the next 2 days because I have like a retreat thing. I was just wondering if, and then you emailed me back saying that's fine. I was just going to rewatch the lectures on YouTube. I just wanted to clarify if those were excused absences or if they counted towards my absence count, because I know on the syllabus we're only allowed 2 absences.
Yeah, you're done. No, those two are, if you don't communicate with me, that's right. And of course, if somebody's communicating with me but missing like 50% of the classes, then that can still be a problem. But as long as there's communication, as long as you're keeping up, you're going to be able to take the quiz. You can still access the quiz and take it, right?
Yep.
Yeah, the quiz is open now, I believe. What time is it? Yeah, it's definitely open now if you want to start it, anybody.
Yep.
Yeah.
Okay. I just want to make sure that I'm not going to be like live on Zoom for the next 2 days, but I'll watch the YouTube lectures every night and then keep up for next week because I know we have the chapter 3 quiz on Monday. So.
Oh yeah.
Okay. All right. Thank you.
You're welcome.
I have a question for the homework 3.1. It asks about a sample space, and I tried looking it up in the book, but it didn't really give a.
Oh yeah, sample space is just a collection of all the things that could happen. So if I have a deck of cards, the sample space would be ace of hearts, 2 of hearts, 3 of hearts, 4 of hearts, blah blah blah, ace of spades, 2 of spades, 3. Just a listing of everything that could happen.
Okay.
Yep.
All right. Thank you.
You're welcome. Hey, Billy, I think everybody's done with questions, maybe? I don't know. Are all these people actually here? All you people there? Anybody? Hello? There's Hannah. Do you have questions, Hannah? Or are you good? Or are you just waiting to see what the questions are so you can listen in?
Yeah, that's I was leeching off of Billy's question.
Oh yeah, sure. Billy, we need you. Billy, don't you lose my number.
Oh, sorry.
That's all right.
Hello.
So what's going on?
So constructing the box plot, for some reason I've gone blank on how to construct them, and I know it's simple.
Can you get the 5-number summary?
Oh, okay. So you get your low, quarter 1, quarter 2, quarter 3, and your high.
Yep. And then
how do I calculate that? I just need to review it. I took shitty notes. It's my fault.
All right. So let's kind of verify this problem here real quick. So they kind of already have the answers there, but let's just see if we can get the same answers. Hold on. Do you see this problem here in the book here?
Yes.
Okay. So they already told us the first quartile is 2, but let's see if we can figure it out. So if I want the first quartile, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 numbers. So how deep into the list do I want to go to get to the first quartile? What percentage of the way?
25%.
Good. So I want to go 25% of 14, because there's 14 numbers. And what is 25% of 14? So if we do
3.5.
Good. Now it's a decimal.
I average that in the number.
No. If you get a whole number, you take that one and average it with the next. If it's anything else, any kind of decimal, you round it up and you take that number. So what's the fourth number? 1, 2, 3, 4. That's why they got the first quartile is 2. Now what about Q2? What would you do for Q2?
B1.
What percentage would you take of 14?
You would take another 4 numbers.
Well, you take half of 14.
Okay.
And Q2 is the second quarter, which is the 50th percentile. Half of 14 is 7. Since that is a whole number, I'm going to take the 7th and 8th numbers and average them. Pretend like that's what that word says. Okay. So what are the 7th and 8th numbers? Let's see. 4, 5, 6, 7, oops. 8. So 6.8 and 7.2. I think that's right. So if I average 6.8 and 7.2, I'm definitely going to get 7, which is what they got here for the median. Now you do the exact same thing for Q3. So look what they did. Hold on, I gotta be able to move this thing. Look what they did. They took first quartile is 2. They put a line at 2. The lowest number is 1. They put a line at 1.
Okay, that's the outlier.
No, it's not the outlier. It's just the lowest number.
Okay.
It's not necessarily an outlier. And the highest number was 11.5. So all you do is, instead of putting like a little dot on the graph, like you're plotting points, you're going to put lines over each of the things, wherever they are, and the middle 3
connect.
Yeah, and then the outer ones are your whiskers.
Okay.
So that's exactly how this is made here. Yeah.
I'm good. I should be able to get through all of it now.
Cool.
All right. Thank you very much for your time.
You're welcome.
I appreciate you.
I appreciate you too.
And putting up with my antics.
Oh, please. I have plenty of my own antics. Is everybody else okay?
All right, later, man.
Take care. I'm going to assume that's a yes. So I'm going to head out. Bye, everybody. Bye, Harris.